All right. The first chapter, which will be the first week, is called Fundamentals of Radiative Transfer. And during this course, you're going to be learning about how radiation is emitted or absorbed. But before you can do calculations of that sort, you need to know some language and some vocabulary which will help you in bookkeeping. And by bookkeeping, I mean how do you calculate how much radiation is emitted? How do you calculate how much radiation is absorbed? How radiation travels through space? Um, how it spreads out in angles, for example, or how it collimates. And to do all of that, you need some vocabulary and you need some mechanism to be able to keep track of where energy is flowing. And so it's good to start with learning to do that. And that's what we're going to start off this week with. The first thing to know is radiation is just energy, right? And this energy can be falling on some area, and then you can ask a question, well, how much energy is falling per unit area? Okay, and that kind of makes sense if you're building a telescope, let's say, and you want to know how big a telescope has to be for you to make a detection. And if you know how much energy falls per unit area, and you know how big your telescope is, you can calculate how much energy you're going to receive with the telescope. So it makes sense to know how much energy falls per unit area. You can ask how much energy is there in direction instead of just on a flat surface. You can ask how much energy is flowing per unit solid angle in some direction. And in the same way, you can say how much energy is being radiated or absorbed or is passing through some area per unit time, right? So time is the third quantity, which is important when you want to do this bookkeeping or accounting of energy. The fourth one is frequency. So you can say how much energy is there per given bandwidth or wavelength range. And so those four things, area, solid angle, time, and frequency, are basically the four axes or dimensions over which you need to do the accounting for how much energy is flowing where. There's a fifth one which comes up now and then, and that's polarization. So if you have two polarization states, you can ask how much energy is there in one versus the other, and that also enters the bookkeeping. If the radiation you're talking about is polarized, and so then the question becomes which polarization, where is the energy, and that becomes important. So just remember these things. These are the axes, as if you may, where we're going to do the accounting. We're going to talk about, the moment I say energy, you need to think about how much energy is it per unit time, how much energy per unit frequency, which direction is it going in, and in that direction, in a given beam solid angle, how much energy there is. And if energy is falling on a surface, then you ask how much energy is there per unit area. Okay, and just keep these things in mind. The moment you have these things, you basically expand out a rich vocabulary, which is widely used, and the meaning of terms ends up being different in different fields. And so instead of just concentrating on learning the names of some terms, it's better to think about what they actually mean and just remember what they actually mean. Because if you go from one field to the other, people might use the same term to mean different things. So for example, the simplest thing you could do is how much energy is emitted by an object per unit time, let's say, and that's called the luminosity. Okay, so that's just the total energy per unit time. In Gaussian units, it'll have a dimension of ergs per second. So ergs is for energy, second is for time. The next quantity you can construct is spectral luminosity. So it's just luminosity per unit frequency. So now you're asking how much energy is being emitted per unit time, but also per unit width in frequency. So now you get ergs per second per hertz. Okay. Another thing which is very commonly used is flux density. And flux density has to do with how much energy is falling on a surface per unit area. Okay, so energy per unit time per unit area is flux density. Spectral flux density, which is sometimes just called flux density, is energy per unit time per unit area per unit frequency. Okay, and the one which is theoretically the most meaningful is the one that accounts for all of these dimensions I spoke about, and that is called specific intensity. So it's energy per unit time, area, frequency, and solid angle. So it has all of those dimensions incorporated in it. And so theoretically, it's the most interesting topic, interesting variable to work with. And the reason is you can follow where the energy is flowing in all of these dimensions along space, angles, time, and frequency. And two other things which we'll come to a little later is absorption and emission coefficient. And so absorption coefficient is basically the fractional change in specific intensity per unit distance. So if you start out with a specific intensity of 100 units, you traveled a centimeter, and then now you're only left with 90 units, the fractional change is 10%, right? So 10 units is what was subtracted in that 1 centimeter, and 10 out of 100 is 10%. And so your absorption coefficient is 10% in that case. And it's always measured per unit length, because if you go longer distances, you'll just absorb more and more. And I'll come to later in the chapter why it is a fractional measure. Why don't you just measure the total amount absorbed? Why are you measuring a fraction of the energy absorbed? We'll come to that later. But for now, just remember that it's the fractional change in specific intensity per unit distance. So it has units of 1/centimeters. The other one is emission coefficient or emissivity, and this just tells you how much energy is being emitted by a particular medium or a group of particles. And that's energy emitted per unit volume, per unit time, per frequency, and solid angle. And that's just emissivity. My experience has been that you don't have to learn these things by heart, because like I said, different fields measure things differently, and they call different things by different names. You don't have to do any of this. You don't have to learn this by heart at all. If you just understand the concepts, right? And whenever you're reading a paper or you're reading a book, just look for the units. The moment you know the units, you know what we're talking about here. You see an equation and you have a quantity and it has units of ergs per second, then you know it's luminosity, right? It's just the total amount of energy per unit time. You might see something which is being called flux density, and let's say it has units of ergs per second per hertz per square centimeter. And so even though they're calling it flux density, it's the spectral flux density, right? So just look for the units, and the moment you know the units, you know what is being talked about. So instead of just learning the names by heart, look for the units and you'll immediately know what is being talked about. Okay, so one thing we would want to do is to be able to convert between these measures. And in doing so, it all comes down to plane geometry. Okay, so think of converting between, let's say, specific intensity to flux density. Think about all of this as basically bookkeeping. Okay, energy is conserved, so all the energy has to go somewhere, and you're basically just doing bookkeeping. But while doing that bookkeeping, you'll have to do some plane geometry. So just to give you an example, let's say you have a bundle of rays. Okay, when I say a bundle, I mean think of it as a ray, like light going in some direction. But you never in reality have light going in exactly one direction. You always have a small width about that direction. So I'll call that a bundle of rays. So just think about a beam of light like you would get from a flashlight, let's say. Okay, so just imagine that a flashlight is shining along this line on the ground here. And notice that we're not shining it, top down vertically. We're shining it at an oblique angle. Let that angle be theta. Okay. And the solid lines here show the total size of the beam, which is falling on the ground. Now, if you ask yourself, what is the amount of energy being received on the ground here per unit area? Okay, that's the important thing, per unit area. You'll notice that that value depends on the angle theta. So for instance, if I shine the light exactly vertically from top down this way, then all of that energy is going to fall on a smaller area here. Okay, so per unit area, there'll be more energy than if I shine it in this oblique way. Now all of that energy is spread out over a much larger area. In fact, you're going to get an ellipse on the ground if you have a circular beam. And so because it's spread out more per unit area, there's less energy. So if you're measuring flux density of this radiation on the ground, you immediately know that it's going to reduce by a factor cos theta. Okay, when theta is 0, cos theta is 1, you get the maximum flux density. For other oblique angles, you're going to get lower flux density. So you'll get lower energy per unit area. And so all of these calculations come down to plain geometry and common sense. So a lot of this is just common sense and bookkeeping. That's what it is. So just to give you an example of how this all works out, suppose I tell you that on the surface of the sun, I tell you what the specific intensity is. I'm going to call it I. Okay, so I is the specific intensity, and that means this is the amount of energy per unit time, per unit frequency, per unit area, and per unit solid angle. Okay, all of those 4 dimensions. And so that's I. And now let's say, imagine you go to the surface of the sun, you draw a small elemental area, okay, of D. This is a tiny area. And then you ask yourself, what is the flux density of the radiation leaving the sun? Okay, so now we are talking about calculating flux density, which is energy per unit time, per unit frequency, per unit area. Okay, no solid angle. So you immediately know that to go from specific intensity, which has a per unit solid angle, to a flux density, which is just per, it doesn't have that unit solid angle, you basically have to integrate over all angles, right? So if you take some quantity which is per unit angle and you integrate out all the angles, then you get the mean value once you've integrated over all angles. So flux density is just specific intensity, which is integrated over all angles. Okay, so let's just do the integration. So again, I'm going to take a tiny bundle of rays which are leaving this surface. There's a small elemental area on the sun. So these bundle of rays are leaving the surface at an angle theta to the normal. Okay, so this is the normal. Now in this bundle of rays, just like I told you, if I'm going to calculate the flux density, because they're leaving at an angle to the surface, there is a geometric foreshortening of cos theta. Okay, so the flux density is just going to be the specific intensity integrated over all solid angles. So d omega is the differential solid angle element. But now I have a factor of cos theta because of the foreshortening, which I just spoke about. So that integral is pretty elementary. You can expand d omega into d phi, d theta, d sine theta. Everything is symmetric about phi. So that integration gives you 2 pi. You only have to integrate over d theta. And here notice that there's only energy leaving the sun. There's no energy going back in. So you only have to integrate over one hemisphere. Okay, so you only go from 0 to pi by 2, because the other pi by 2 to pi is in the hemisphere facing the sun. But all the energy is going in one direction. It's leaving. So it's only half the hemisphere where the ray bundles are leaving in different directions. Okay, so and the cos theta is the cos theta factor. And that's pretty elementary to do. You get pi times I. So that means that if I give you the specific intensity, you can calculate the flux density on the surface of the sun. Okay, we'll do another problem in class, and that has to do with a classical pinhole camera. It's a classical problem of image projection. Well, again, these kind of factors are going to come in, and this kind of bookkeeping is going to come in. Okay, so one more concept which is worth knowing is what is called the constancy of specific intensity. I think it's also called the conservation of étendue. I don't know if I'm pronouncing that right. But the idea is this. If there is no absorption or emission in a medium, it's just radiation propagating, then specific intensity along the ray is constant. Okay, so what this means is, let's say you're following the ray. As the radiation is light is propagating, you're following that ray. The specific intensity at each point is always constant. Okay, so remember in this problem, I told you that the specific intensity on the surface of the sun is I. If this theorem is true, and I'll show that this is true, then the specific intensity of the sun on the earth is also I, because you're just following rays coming from the sun to the earth, and specific intensity does not change. So that value I is going to be the same whether you're on the sun or you're on the earth. That I is not going to change. Okay, so let's go through this. Again, all of this just comes down to bookkeeping. So the problem is defined as follows. Let's say you have a ray that is moving horizontally here. Okay, and I'm going to take two small differential area elements, dA1 at this point here, And along the ray, a further distance out, I'm going to take an element dA2. Okay. And then I'm going to basically say that I1 is the specific intensity here, and I'm going to try to calculate the specific intensity here, I2, and I'll end up with the result that I2 is equal to I1, regardless of this distance. So that means that for any distance you travel along the ray, the specific intensity does not change. So let's go through that. So we want to calculate I2, that is specific intensity at point 2 here. And that is just the flux density here. So this is the energy per unit area divided by the beam solid angle of the radiation. And that is d omega 2. So that is just this angle, d omega 2. So this is the angle subtended by the source here. So you can think of this as the source of the energy. The angle subtended by the source, d omega 2, is the range of solid angles through which radiation can cut through this area dA2, right? So these are all this is the range of possible angles over which rays which are coming from this source plane can cut through this area. So F2 divided by d omega 2 is the specific intensity. Now you can ask yourself, what is F2 itself? Okay, so F2 itself is basically the flux density on this surface, right? So it's the total energy that is going through this surface divided by the area of the surface. Okay, so the denominator is the area dA2, and the numerator should be the total amount of energy that is going through this surface. Now, what's the total amount of energy per unit area? Sorry, it's a flux density. So energy per unit area going through this surface. Yeah, so we already have that in the denominator, sorry. So dA2 is the denominator, which is the area. So the numerator is just the total energy going through this surface. So what's the total energy? Again, this is the source of the rays. The rays are coming from here. I1 is the specific intensity. And I'm going to multiply that by d omega 1. So d omega 1 is all the range of angles over which the rays which are entering the source will also cut through this area. So I1 times d omega 1 times the total area here is the total amount of energy of the radiation that is going through dA2, right? So just check the units. So I1 is going to be per unit area per unit solid angle, and you multiply that by d omega 1 dA1. So you just get energy units here. And then in the denominator, you have area. So it's energy per unit area. So that's flux density, right? And so you have basically the proof. So you just get rid of F2 from these two equations. And you know that d omega 1 dA1 should be equal to d omega 2 dA2. That is just plain geometry. That's the relationship between the area subtended by a beam solid angle. Both of these are going to be r square, and they're going to cancel out. R is the distance between these two planes. And so you get I2 equal to I1. And so that's a very handy thing to know. It tells you that I is always conserved. Okay, so unless there's something funny going on in the medium here, like there's some emission or absorption going on here, as long as that's not happening, I is always conserved. And that's good to know. It's always good to know conserved quantities because it simplifies a lot of the calculations. And this is why I said earlier that specific intensity is an important quantity, because specific intensity is always conserved. So whenever you do radiative transfer, so when you're trying to follow radiation as it goes through a medium, you always look for what is happening to the specific intensity. If the medium does nothing and behaves like vacuum, then whatever I you put in, the same I comes out. If the medium has absorption, I is going to reduce. If the medium has emission, I is going to increase. And later we'll get to the equation of radiative transfer, which just tells you how I varies when radiation goes through a medium, which might be absorbing and emitting. And so I is the theoretically interesting quantity. And this is also the quantity that will appear in Planck's law, as we'll see later. Okay, so that was about the vocabulary and just basically introducing the names and the meanings of variables which we'll be using.